it has an anomalous quantum Hall effect. It has some things that you don't see in other systems. So, there's interesting physics there. I would say it's not necessarily more interesting than nanotubes, but nanotubes are now, 15, 20 years old, right? So it's new. Does that sort of answer? So I don't know. So my feeling on graphene is that it's an easily obtainable material that you can publish in, that you might as well do, and that has probably 5% of the current papers are really interesting and new, but that's a pretty good fraction. Yeah.
For these small electronics with the carbon nanotubes,
yes.
They perform a lot better at low temperatures. So for that, would that mean to build a quantum computer, you'd have to keep it at a low temperature?
That's right. Yeah, that's an excellent question. So the quantum properties show up at low temperatures. So the answer is yes. In general, to build a quantum computer for using these sort of materials, you'd have to do it at relatively low temperatures. Now, nanotubes have an advantage compared to other systems, is that, as you know, quantum properties show up more if you're smaller, right? So atoms show quantum properties at room temperature, right? So nanotubes are so small that you can actually see a lot of these quantum effects at, say, 80 Kelvin. So you can use liquid nitrogen to cool them down as opposed to liquid helium. So they might be cheaper to operate than other systems that really require helium or specialized fridges. So it's possible you still have to cool it, but maybe not as much as you would other systems that are bigger to use. But yeah, I mean, you'd have to cool it down, and then there's all sorts of, there's still, in any solid state system you want to make a quantum computer with, you always worry about external influences that kill your quantum properties or kill your coherent properties. This can be noise, this can be thermal effects, this can be connections to other things. That's just a huge issue in the field. So yeah, I don't suspect you'll see a quantum computer in the next 20 years, right, is my feeling, but maybe later, I don't know. Yeah.
With that low temperature effects and how that makes it more beneficial, would there be more applications for this, like sort of astronomically, like space and satellites type of stuff, where you have fewer external effects to deal with? Is that the primary, like, sort of trajectory of this research?
That's a great question. The answer is, I think for things like quantum computers, it's an interesting thing. There's no really killer applications yet for these things. And I suspect if they made one, they'd find out how to do it. But everyone says, oh, you can solve algorithms, right? Well, I don't know. I don't see it's not like the economy is now down the tubes. We haven't solved enough algorithms, right? Probably quite the opposite. We solved way too many algorithms, right? and it's been a big problem. So. So I think that the applications will likely be, more for quantum computers and that sort of thing would be more Earth-based computer science applications, probably very specialized, traveling salesman-like problems, which are big deals for a lot of companies, but those sort of things. Space does have low temperatures, but it'd be very different unless we're actually going to make a base or something. You don't gain. It's so expensive to go to space. I think you might as well just use liquid helium here on Earth. Yeah, I think, yeah. Also, it's funny. I don't know if you followed any of the space research. People have thought of putting things in space where it's cold and they can operate cheaply. The problem is that if you're near, if you're operating in space and you need someone to handle it, it has to be near a rocket ship of some sort, right? And those things are hot and dirty, right? So you actually want something to operate in space very, very far from your ship. The closer you are to the ship where you can actually handle it, the more you're getting fuel emissions and radiative heat and other things like that. So it's actually a little bit of a catch to think about operating in space. Unless you can leave it on a base alone and have it transmit, you're not really gaining that much. But, yeah. Yeah.
Somehow, in the sense of these kind of materials, they said that they might not seem up to asbestos to issue. How do you deal with that?
Right. So do you mean how do we deal with it in the lab, or how does one deal with it in general? Yeah, that's a great question. Yeah, it's interesting. This is, as scientists, I guess, as scientists, it's always a challenge to sort of push the best science you can as fast as you can and get the interesting results, and still be a responsible human being in terms of what is the ultimate effect of your research, what is the ultimate effect of the materials that you're creating, what are the other things that are happening here. In this case, there's been some work on the studies of the hazards of nanomaterials. I mean, there's no known, I've looked at some of these studies, and to me, it's hard to tell what the real effect is. But for sure, things like nanotubes are shaped like asbestos rods. Do you think you don't want to breathe these things in? In my lab, we deal with extremely small quantities. If you saw the chips that we deal with, they're sort of half-centimeter chips with, we actually want to contact these. They might have 10 nanotubes on them. So, I tell my students not to put their noses in the oven after they've grown, but usually these things are pumped out at the other end. They have gas throwing through. So as long as I feel like they're not breathing in the oven, they're just dealing with small quantities, it's probably okay. There are companies that make barrelfuls of these, and I'm not quite sure what they do. I've heard, there's conflicting evidence. On one hand, people are using things like nanotubes to directly target cancer cells, right? They're injecting it into animals, and these things tend to go to the cancer cells, and they seem to be helping. On the other hand, they inject it into the gills of fish, and they get clogged up, and the fish can't breathe anymore. I mean, we don't have gills, that won't happen, I don't think, right? But it's not a great sign. So it's really mixed right now, and I guess the most we can do is be sort of be aware of this and try to be careful. In terms of breathing in and handling it, wash your hands, that sort of thing, and yeah. But
I got a question.
Yeah.
So, the sizes of these nanotubes, right? Are they controlled by chemistry when you're making them?
Yeah.
Or so can you control the size of the diameter?
Yeah, that's a fantastic question, and the answer is yes. So nanotubes are a great field in that chemists and material scientists and physicists work together on these. So chemists are the ones who really discovered this and who've been working on the side of controlling their diameters. So yes, there are certain recipes, growth recipes, that tend to make smaller or larger diameter tubes. There are growth recipes that tend to make longer or shorter tubes, or that make multi-wall versus single-wall tubes. Even some recipes that tend to make more metallic or more semiconducting tubes. And so people are really hard at work on doing these sort of things. And they're somewhat successful. So I would say if you use a recipe that tends to make large diameter tubes, maybe you'll get 50% large diameter tubes, which is much better than you usually would, but it's not quite enough for industrial applications, right? You'd still have to have another process of centrifuging or something to separate these things out. But the answer is yes, it's a huge project in itself to control these things. And I've had students in my lab try to do it, and I feel bad. So every time a student comes to work for me and they do nanotubes, they say, well, why don't I just fix the recipe and do this or that? And I say, that's a research project in itself. I want you to measure them, not just make them. Right? So you sort of need to work very closely with people who make them. And
so why are they around? I guess what's the driving force for them? I mean, I don't know.
How do you roll them out?
Yeah, I don't know what the driving force is, but I mean, energetically, it's a stable configuration, I guess. So let's. So you have to have. Obviously, you have to match a carbon atom, or you can't just connect it any which way. But when they're actually rolled up, it's a stable. It's a crystal, right? So there's some. Let's see. There's some.
So they have to roll practically. You can't have a sheet.
They don't. Let's see. They don't. I see what you're saying. They don't start as sheets. They start as. Where do I have a growth here? They don't start as sheets. So when you grow nanotubes, you're not actually starting from graphene. Yeah. They're growing. So I think they start with the way they grow. And there's still some controversy as to how these things grow.